In my previous video, I recalled the definition of Cheeger space as all LP functions for which there is a sequence fi with upper gradients gi that are also in LP, such that fi converge in LP to f and that the LP norm of gi remain bounded. In particular, there is no convergence assumption on these derivatives, on these gi's. Then we equip this space with the norm that you see here. Now the question is, when f is in H1P, does it have any derivative in some sense? Can we produce something out of these gi's really? And that's true for p bigger than 1, which is the content of this video. If f is in H1P, then we can improve the sequences in the definition to require that actually the gradient parts also converge in LP. Norm of f1p is defined through an infimum. So we can pick sequences that minimize, that go toward this infimum. So we do have fi and their upper gradients gi such that this fi LP, or let's just go directly to f, plus limit, and we can also assume that this converges by passing to subsequence, so no liminf, that this gi LP equals the f of 1p. So we're basically saying that let's choose a minimizing sequence of fi and its upper gradients. So these gi's provide the smallest LP norm. Claim, the biggest part of this claim is that from this we actually, gi themselves converge in the strongest sense in LP. And this is kind of a kind of amazing fact that from convergence of norms, you're concluding convergence of sequences. It's imagine like in complex, even in complex plane, you have a sequence of zi that you know that a norm converges to 1. Can you claim that zi themselves converge to 1? No, because they could be here, they could be here. Anywhere on the surface will do it. And we're not even claiming that the gi has a subsequence that converge. We are claiming that the whole thing converges to a limit. The reason this holds is due to two facts: uniform convexity and properties of upper gradients. Remember, these gi's are not just any functions, they are upper gradients. We need to show, or it suffices, it is enough to show that gi are Cauchy in LP, of course. Suppose otherwise, suppose it was not. Then, after choosing subsequences and relabeling, we produce this fi tilde. This is one branch with upper gradients gi tilde. These are exactly one of the elements in the original sequence. And the other branch, double tilde, with upper gradients gi tilde, such that, so not Cauchy, that means gi and gi, gi double tilde and gi hate each other by this delta. That means first we have to say there is a delta positive. So if they are not Cauchy, that means there is a delta positive, and there are points that just bounce away from each other by this much. Then we build a new sequence. Then fi tilde plus fi double tilde over 2. Here is where we use the facts about upper gradients. Have upper gradients that are gi plus gi double tilde over 2. So any linear combination of upper gradients will be an upper gradient for the same linear combination of the corresponding functions. Easy facts to prove from definitions. And well, these guys, fi tilde, each one of them is a subsequence of original f. These converge in LP to f. So by definition of a norm of H1P, F norm is less than, so we have one particular choice of upper gradients. This will be less than norm of F plus limit as I goes to infinity of norm LP of the upper gradients gi tilde plus I double tilde. But then this will be strictly less because of uniform convexity. These converge to that circle sphere, and then they are delta apart with delta independent of I. Therefore, this quantity, this LP norm, is strictly into the ball, is less than that. So this will make it strictly less than norm of F plus, did we give this a name? So yeah, with C I mean, suppose this limit is just C. So this will be norm of FP, LP plus C. And this is by assumption the norm of F1P, and that's a contradiction. So F1P is strictly less than F1P. So this contradiction shows that no two subsequences of GI can remain delta apart. Hence, GI is Cauchy. And because LP is a complete Banach space, there exists G in LP such that GI converge to G in LP. And if now you converge in LP, then your norm also converges. Therefore, this last bit holds automatically, because the C becomes norm of G. Yeah, and this is amazing. So because of the fact that we can do a convex combination of upper gradients, and because of uniform convexity, we end up proving convergence in the strongest sense of GI. Maybe we could actually add this bit to this also. Again, in the paper, of course, they do it. Such G is unique as an element in LP. So you can change it up to measure 0. But why is that true? Uniqueness of G is from exact same argument. If you had two G's, like you had one sequence going to this G and then another one was going to another G, then you could do one by one linear combination, and then you will enter inside the ball. So that would again violate the minimality. Then you would be able to find a new sequence whose LP norms are even smaller. What Cheeger does is define H1P through and apparently too relaxed a definition, use functional analysis magic to prove much more. And then also this object, the unique object G that we find, G as above, is called a minimal generalized upper gradient. So our question is answered. Every F in H1P has a unique object G attached to it, which is called the minimal generalized upper gradient. So that is in this sense that we can say the creatures in H1P are still differentiable in some sense. This is a great paper of Cheeger. I'm still reading it very patiently and carefully, doing a lot of examples for myself and exercises. So if you have questions, please do put them in the comment and I will think about them. And if anything comes interesting out of them, I will I'll be glad to investigate and share my findings with you. Thank you so much and have a lovely weekend.